Now we talk about weak approximation theorem. So let these be bunch of non-trivial and pairwise inequivalent absolute values. So you have n absolute values and none of them are equivalent to each other. So they are pairwise inequivalent on some field k. And then say we are given these elements of field k, a1, a2 all the way to an in k, and there is some epsilon greater than 0 given to you, then there exists an alpha in k. So there is another alpha in k such that alpha minus ai, and then you take absolute value I is less than epsilon. So that is, we can approximate all these numbers by a single alpha in all these absolute values, and this is true for all valuations I. So I is 1, 2, 3 all the way to n. So you can see again it is simultaneous approximation of all these elements by a single element using different valuations. So this theorem critically depends upon another theorem, and the first line of the theorem is same again. So let these be a bunch of n absolute values, each of them is non-trivial and any two of them are inequivalent to each other. So pairwise inequivalent absolute values on a field k. So first line we have just copied as such. So then for any I where I lies between 1 and n, that is for any of these absolute values, there exists some number ai and k such that if you take its ith valuation, this is I, and you take the ith valuation, it is greater than 1, and for other it is less than 1. So for a single valuation it is greater than 1. These indices should match, and if these indices do not match, then it is less than 1. So we will prove this theorem later, but using this theorem let us prove the approximation theorem. So if you assume this theorem, so then there is existing some element beta I, so instead of ai we are writing beta I, such that beta I is greater than 1. So just copying this right here and copying this right here. So beta I evaluated at k is less than 1. So now consider this number here, that is ai times beta I r over 1 plus beta I r, and evaluated at I. So that means this, when you start evaluating it, this thing is greater than 1. So you take r going to infinity. So as r goes to infinity, this fraction is going to go to 1. So this entire thing will go to ai, or you can say absolute value of ai. Really doesn't matter. So this is for greater than 1 because you had I inside and I outside, but now you have I inside and k outside, so this is less than 1. So this fraction would go to 0 as r goes to infinity. So this entire thing will go to 0. So for a big enough r, we can make this as close to ai, and we can make this fraction as close to 0 as we wish to. So therefore, if you take the sum like this and evaluate it at j, so the only thing which will remain is when the index here would match j, all other terms in the summation will go to 0. So this will go to aj, or you can say absolute value of this at j, where j lies between 1 and n. So now it is easy to prove such a theorem because you will just say alpha is equal to precisely this summation, because this will go to aj when these two indices match. So for any epsilon greater than 0, you take r sufficiently large so that alpha minus this is less than epsilon, precisely because these two indices are matching. So if from here, if you subtract this out, all other terms are going to go to 0 because this was the only term which was going here. Because of this, all other terms will have something like this. You have I here and k here, or I here and k here. These indices are not matching, so they will go to 0. So only non-zero term we have subtracted out, and that is why we have less than epsilon. So this is a easy proof depending upon this theorem. So the only thing we have to think about is this fraction, and in fact this fraction is the most critical part, and this will be used in the proof of this theorem also. So now let us prove this theorem, which will complete the proof for the approximation theorem. So this is what we wanted to show here. So now we are going to prove this theorem. Again, we have n absolute values. All of them are non-trivial and they are not equivalent to each other. So then for any I, that is for any absolute value, there exists some number ai like this, such that you take absolute value of ai at I, this is greater than 1, and for I not equal to k, this is less than 1. So this is what we want to show. So we are just going to prove for I equals to 1, and you can repeat the same case n times. So what we are going to show is that there is some number a in k, so there is some a lying in field k such that absolute value of this a with respect to valuation 1 is greater than 1, and absolute value with respect to valuation k is less than 1 for every k greater than 1. So in fact what we are going to do is we are going to construct some r like this and say if you set a equals to ar, we get the first absolute value is greater than 1 and all other absolute values are less than 1. And this you can do for any I, so the theorem would be proved. So we have to go from here all the way to the end of the proof, which will be here. So we have to construct this R, and we are going to use induction. So since we want to use induction, we have to start with the case 2. So we will prove for n equals to 2 first, and then make the inductive assumption. So for n equals to 2, first recall the definition of equivalent absolute values. So we have proven this in previous lectures that two values are equivalent absolute values if the first valuation is less than 1, if and only if second valuation is less than 1. So then these two are equivalent. Here we are saying these are inequivalent absolute values. So inequivalent means that the say first one is less than 1, then second one is greater or equal to 1. So this is equivalent, so we are making it inequivalent. So we have say two inequivalent valuations, and then there is another element y for which again these two valuations are inequivalent. So here it is less than 1, the first valuation is less than 1. Here the y's first valuation is greater or equal to 1. Here second valuation is greater or equal to 1. Here the second valuation is less than 1. But they are inequivalent for some x, y and k, and this is what the inequivalent valuation or absolute value condition is. So now we put a equals to y x minus 1. So absolute value of a, this will be equal to, and then you have this. So what is the first valuation? So first valuation is greater or equal to 1. So this is greater or equal to 1, and first valuation of this is less than 1. So inverse of would be, so since we have inverse, so inverse would be greater or equal to 1. So you multiply two values greater or equal to 1, you get this greater than 1. Similarly, other way around, second valuation would be less than 1. So we have been able to show that result holds for n equals to 2. If you take two absolute values which are inequivalent to each other, we do get the absolute value of a with respect to this 1 is greater than 1, and absolute value with respect to 2 is less than 1. So result holds for n equals to 2, and now you assume that it holds for n minus 1 greater or equal to 2. So now you will have say two elements. So you say you have an element c. So for c we just have two valuations. So say the first valuation we can assume that it is greater than 1, and the nth valuation is less than 1. We do not know what is happening to the other valuations between 1 and n. So we do not know what is 2, 3, 4 all the way to n minus 1. But these two it will hold for. So this is good. And similarly we can make inductive assumption for an element b. So the first valuation is greater than 1, and 2 is less than 1, 3 is less than 1, all the way to n minus 1 is less than 1. So these are the two assumptions we are making. One for element c, which is just two valuations, and rest for n minus 1. So anyway, you could have made it for 2 because 2 is less than or equal to n minus 1. So now we distinguish two cases. In the first case, absolute value of b of n would be less than equal to 1, and in the second case, absolute value of bn would be greater than 1. So those two cases will cover everything. So from here we will have to go to here, or we can say right here. So from here we have to go to here, and this will be easy to see. So absolute value of b with respect to this n is less than or equal to 1. Now you set AR as b to the power of r c. So you take absolute values for I, it will look like this. So by hypothesis, this is greater than 1 for I equals to 1, because for valuation 1 it is greater than 1, here also it is greater than 1. So this thing would be greater than 1. So we have been able to show now for valuation 1 it is greater than 1. For all other valuations we want it to be less than 1, like this. So if I is greater than 1, this would be less than 1, precisely because these b's are less than 1, and we are saying bn is also less than or equal to 1, and you're raising it to the power of r. So for the nth term this could be 1, but then cn is less than 1, so this would be less than 1. For all other terms we do not know what c is going to be, because we do not know this absolute value of c with respect to 2, 3, but we know this is going to be less than 1. So if this is going to be less than 1 and this is just going to be a number, you have raised it to the power of r, you can take r big enough, and since this is going to be less than 1 raised to some r, if r is big enough this will go to 0. So you can choose r big enough to make this as small as possible you want. So we choose r big enough to make all other valuations less than 1, simply because all these are less than 1. And for nth it is easy, even if bn is 1, then this cn is less than 1. So yeah, so you choose a suitable r and put a equals to ar. So from here you can go to here, just because of this valuation. So holds for 1, holds for n, and for rest you use the limiting thing. Now case 2, these are only two cases, it's less than or equal to 1 and greater than 1. So now we set AR as this PR over 1 plus PR times C. So now between 2 and n minus 1, all these valuations are less than 1. So between 2 and n minus 1, all these valuations are less than 1. So for a large R, you can take, as R goes to infinity, this will go to 0. So no matter what C is, you can take R large enough to make this ARI less than 1. So for this absolute value 2, absolute value 3, and so on, to all the way to n minus 1, we have been able to show that it is less than 1. So what we need to now consider is case 1 and n. So for case 1 we want to show it is greater than 1, and case n we want to show it is less than 1. So for case 1, this valuation bi is greater than 1. So this is greater than 1, as you can see. So if this is greater than 1, as r goes to infinity, this thing is going to go to 1. So AR is going to go to C. So this is going to go to C, but you can see the valuation of C is greater than 1. So if you take I as 1, this is greater than 1. And if you take valuation n here, then you get absolute value of this Cn, which is less than 1. And that's what we wanted to show. This is going to this valuation is greater than 1 or it is less than 1. So you have this or this. What you just have to do is choose a suitably big enough value for r, so that you can set a equals to ar, and then these conditions would hold, because this will approach this. So you can just take an r big enough so that it is greater than 1 and less than 1. And that is the end of the story. That is precisely what we wanted to show for this theorem.